Hello students, my name is Ashwani. I am from DAVIET JALANDHAR. Today I am going to give you a lecture on numerical solutions of differential equations. In your previous unit, many differential equations are not solvable easily by direct methods. So for solution of such differential equations, we take approach of numerical methods. Although results are not accurate, but matters a lot because at least they have solutions. Numerical methods are well known for their easy algorithmic approach to find solution. It can easily find the solutions of difficult differential equations. These are so effective because not only ordinary differential equations but partial differential equations can be solved easily by these numerical methods. Some prelims. When you solve differential equations, you have two types of problems. Namely, one is initial value problem and another one is boundary value problem. Now what are these? Initial value problems are those problems in which we have to solve one differential equation in which initial condition is given only. That means you can see this is your differential equation and this differential equation has only one initial point. That means this is initial value problem. But if your differential equation is equipped with initial as well as final condition, then that problem is known to be boundary value problems. We have two types of methods to solve initial value problems, mainly single step methods and multi-step methods. Now, what are single step methods? In these methods, we solve initial value problem as values y0, y1, y2 and so on up to y. Y0 is given to us. With the help of y0 and x0, we will find y1. Similarly, with the help of x1 and y1, we will find y2 and so on. So that's why these are called single step method, because these methods use previous step values to find the next step values. In these methods, we can increase the accuracy by decreasing the step size also. So this is one working chart of single step methods. You can see this x0 and y0 is given to us. With the help of this x0 and y0, we will find x1 and y1, and with the help of this x1 and y1 we will find y2 and so on. So this is the working procedure of all single step methods. Various single step methods includes Euler methods. Euler methods is of three types: Euler method itself, Euler improved method and Euler modified method. Other methods are Taylor series method and Runge-Kutta methods. Euler method. This is the simplest method to find solution of differential equations. In this method, we use x0, y0 and we find the value of y1 by simple Taylor series formula. Now in your previous classes, y1 is what? Y at x0 plus h, because x1 is x0 plus h. Right? If you just open the Taylor series formula for only one term, you will get y0 plus h y0 dash. Right? Now here y0 dash is given to you as your differential equation. So if you just substitute y0, x0, y0 in this, you will get the formula x0 plus h f of x0, y0. Similarly, you can evaluate the formula for y2 as well. So y2 will become y1 plus h f of x1, y1. So we have generalized that formula as yi plus 1 is equal to yi plus h f of xi, yi. This is the working procedure. Graphically, we have shown this. Here, xn and yn is given to you. Now, at this point, x and yn, we will find the slope at the curve, and this slope is meeting here. So this becomes your yn plus 1. Now, again, at this point, yn plus 1, we will find the slope at this curve. Say direction is similar to this, parallel to this. So this point will become yn plus 2. In the similar way, we can find further yn plus 3 and so on. Euler's modification. Euler has two types of modifications. One is improved Euler method and one is modified Euler method. In the improved Euler method, Euler modified the value by taking the average of the slopes instead of taking the just slope at x0 y0. So he improved the accuracy. But in modified Euler method, instead of taking the average of slopes, he had taken the averages of the step sizes. So you can see here the step size of x taken to be half, and whereas step size of y, this is step size of x, and this step size of y taken to be half along y. So this is working graphical in interpretation of Euler's modifications. First of all, improved Euler method, you can see this is your slope at this xn yn, or you can say xi ya, and this is slope at xi plus 1 ya plus 1. Now these two slopes, we have taken the average of these two slopes, and say suppose this is your slope, average slope. So we have calculated that slope at this x0 and y0, and in the direction we have found this ya plus 1 with the help of this average slope. So this is the criteria of Euler's improved formula. Whereas in the modified Euler's formula, here suppose this is your xi ya, we have found slope at this point. So now what we have done, we have taken the half step. This is our half step. Now at this half step, we have calculated the slope at the curve. Now at just parallel to this, we have calculated the slope of the curve, and along this direction, along this slope, we have found the value ya plus 1 with the help of this average slope. So this is the criteria of modified Euler method. So you can understand easily. In the improved Euler method, we have taken the averages of slopes, whereas in the modified Euler method, we have taken the half step of the xi plus 1 interval. Let us solve few examples for Euler methods. First of all, let us solve an example for Euler method. So this is one example given to us. dy by dx equals to y minus x over y plus x. The initial condition given to be x at x0 0, y0 is 1, and we have to take the step size h equals to 0.1. So we have calculated with the formula. What is our formula? y1 equals to y0 plus h f of x0 y0. Now x0 is given to us and y0 is given to us. So with the help of x0 and y0, we have calculated the slope. Slope is y minus x over y plus x. So we have substituted these values here. So we get y1 equals to 1.1. Now in this example, we have also demonstrated that how step size accurates the value. So in the next step, we are going to demonstrate this. What we have done, from 0 to 0.1, instead of taking one step, we have taken 5 steps. So you can see we have taken the step size 0.02. So the 5 steps will become, first we have 0, then we have the next step 0.02, then we have the next step 0.04, then we have next step 0.06, then we have next step 0.08, and at last we have the last step 0.1, right? So one by one we have calculated all these values. First of all, y1 is y0 plus h f of x0 y0. We have substituted all the values and get the value of y1. So with the help of this y1, we have then evaluated the value of y2. तो y2 का फॉर्मूला आ गया, y2 is y1 plus h f of x1 y1. So values डालने के बाद 1.02 plus 0.02. So all the values we have substituted and calculated the value of y2, that is 1.0392. Right? In the similar way, we have found the values of y3 and y4 and y5. So this become our y1, this become our y2, this become our y3, y4 and y5. So you can see if we have taken the step size 0.1, the value comes out to be 1.1. So if we have taken the step size 0.02, the value at 0.1 is 1.0928, which is more accurate as compared to 1.1. So that's why if we decrease the step size, we will get the more accurate values, right? Next. Now this is next example, which is we have solved with the method improved Euler method. In this example, we have given the slope log x plus y, and we have given the initial condition x0 per y1, right? So now what is the Euler improved method? In the Euler improved method, first of all we will calculate y1, right? After finding y1, we will find the this you can say also prediction correction method, because in this method first of all we will predict the value and then we will correct the value. So that's why this method is also known as predictor corrected method. Okay. So this is our prediction. First of all, this we have done as similar to Euler's method, right? So after prediction of this, we have applied the Euler's improved method. This is our Euler's improved method. So in this formula, we have substituted all the values. We know what is x naught. X naught is 0, y naught is 1, right? In the next, we have calculated value of y1. So this y1 and these values we substituted in this formula to get the value of y1 corrected value using improved Euler method. Now further you can also improve this value, right? What you can do, you can substitute this y12 instead of this y11 here in the same formula, right? That means instead of this y11 you can substitute this y12 to correct the value, right? So this become your more corrected value. You can repeat this step until you get the stable value. Now you can see at the fourth level we get the value 1.049914, and in the previous step we have calculated the value 1.049816. If you take 4 places of decimal, you can see the value is stable. So this is our result as Euler's improved method. Now next we have an example by modified Euler method. So in the modified Euler method, what we have learned, that we will divide the step. We will not take the average of slope, we will divide the step, we will take the half step. So in this question, we have given the slope e raised per x plus xy, and the initial condition is at x0 we have y0, and we have to compute the value of y at 0.1 and y at 0.2. So let us start. We know what is the method of Euler's modified rule. The Euler's modified rule is y1 equals to y0 plus h f of x0 plus, now see this is half step. So similarly this is half step along y. So that's why Euler's modified use the rule of taking half step as compared to Euler's improved rule, which takes average of the slopes, right? So all the values we know, h 0.1, y x0 0, y0 0. Substitute all these values here in the formula, you will get the value of y1. So this will become your value y at 0.1. Now as per question we have found 0.1. Now we have to find y 0.2. So for that we get the value for y2 as well. This is the formula for y2, right, with the help of y1. So substitute all these values. This is your y1, this is h, right? All the values you substitute here and calculate the value, you will get the value y 0.2, right? These methods are very easy because Euler's methods are the, you can say, the first category which is used to solve differential equations. Next we have taken one example in which we have compared all these three methods together. That is Euler's method, modified Euler's method, and improved Euler method. So in this example, what we have done, first of all, what we have given, we have to find the values of y 0.2 and y 0.5, where slope is given to be 3xk plus y. Initial condition is given to be at x0, y is given to be 4, right? Now I am just leaving this part of solution up to the students. They can calculate these as we have done in the previous examples. So I have left this for your practice. You can calculate it and compare the results with my results, right? Now see what happened. When we calculated the values with Euler formula, we are having the values 5 and 6.2969. With the way of modified, the values are 5.1367 and 6.6913. Whereas with the help of improved Euler's method, we have found the values 5.1484 and 6.7194. Whereas we have also calculated the exact values. The exact values are 5.1528 and 6.7372. Now from this comparison you can easily analyze that which method is more accurate, which method is more closer to the exact solution. So you can see yourself that improved Euler method is more accurate as compared to modified and as compared to Euler method, right? So this is one comparison between the three methods which tells you exactly what is the exact method. So you can see yourself this comparison. With the help of this comparison, we have easily seen that Euler improved method is more accurate. So next single step method is Taylor series method. Now you know in your previous classes earlier in plus 2 as well as in BTech first year, semester 1 class, where you have learned calculus, that what is Taylor series. Taylor series is the approximation of the values near to the values what we know. So in this method, here y is given to you at x0, right? Now x1 is what? X1 is the neighboring value of x0 at a step size of h. So we can calculate the value of y at this neighboring point x0 plus h with the help of Taylor series method. So in your previous classes, as you have expanded the series, what will be the series? Y at x0 plus h will be equal to y0 plus h y dash plus h square by 2 factorial y double dash plus h cube by 3 factorial y triple dash and so on. So this is your Taylor series, standard Taylor series, as you have learnt in your previous classes. So we will use this methodology to calculate the values for our solutions, and this method is called Taylor series method. So for example, say suppose this is your initial value problem in which this is your slope x plus y, this is your initial condition. At x0 we have given the value of y to be 1. Now we have calculated the value of x equal to 1.2 with a step size h 0.1. Now what is the meaning of step size 0.1? We have given the value of x equal to 1. That means we will take the two steps. First of all, we will calculate the value for 1.1 and then we will calculate the value of 1.2 with the help of 1.1. So let us find first of all first step at which x0 is 1 and y0 is 0. Now see, this is what? Y dash. So y dash is x plus y. What we will do, we will take the derivatives with respect to x with the help of this y dash. So you can easily see y dash is x plus y. That means y double dash is 1 plus y dash. Take the third derivative, that will be y double dash. Take the fourth derivative, that is y triple dash, and so on. Number of derivatives increases the accuracy of this method. as much as derivative you will take, you will find more accurate values, right? So after getting all these derivatives, what we will do? We will find the values of these all. See, this is your x naught and this is your y naught. Now, what is y naught dash? Y naught dash is the value of slope at the point x naught, y naught. So this is your value, right? You just substitute the value of x naught and y naught here, you will get the value of y naught dash. Similarly, when you substitute the values of y naught dash and x naught as well as y naught, you will get the value of y naught double dash. So you substitute the values, you will get the y naught double dash. So by substituting all these values one by one, you will get the values of derivatives, right? So as per formula which we have done here, see again, this is your formula. Now here x naught plus h is known to be x1. So y at x1, this y at x1 is what? y1. So this point we have taken as y1, whereas this is y0. Now if we calculate the value of y dash at x0, we will get y0 dash. If we calculate the value of y double dash at x0, we will get y0 double dash, and so on. So our formula becomes y1 equals to y0 plus h y0 dash plus h square y2 factorial y0 double dash, and so on, right? Now all the values you have calculated here. See, you know what is h, you know what are y0 dash, y0 double dash, y0 triple dash, and so on. As much as derivatives you will take, you will get more accurate values. So substitute all the values here, you will get the value of y 1.1. Now this y 1.1 become your y1 now. Now what is x1? x1 is x0 plus h. So x1 become 1.1. In the similar way, as you have calculated the derivatives here, you can calculate the derivatives of y1 dash, y1 double dash, all these values by substituting x1 y1 in place of x0 y0, as you have done in the previous step. So calculate all the derivatives. Now you can see, now this is your y1. So y1 plus h become y2. So y2 is y1 plus h y1 dash plus h square y2 factorial y1 double dash, and so on. That means 0 replaced by 1 now, because you have to find the value of y2 with the help of y1. So all the derivatives you have calculated, all the values you have calculated, like triple derivative, fourth derivative, and in the previous step you have calculated other values. Substitute all these values here, you will get the value of y2. So this is your y2. Now also we have calculated the analytic solution as you have done in your previous unit number 1. So analytic solution comes out to be this one. If you just substitute the value y 1.2, that means x key value 1.2, if you substitute here, you will get the result 0.2428. Now just see, this is your accurate exact result and this is your calculated result. So you can find error also by taking the difference between them, right? So this shows that if you use Taylor series method, you can get the accurate values. Not accurate, but ठीक है, 0.2428 and 0.232 is near to 0.2428, and when we solve systems, when we solve physical systems, then approximate values are good enough. Another example. So again I have left this part, this solution part, for students for practice purpose. So you can calculate yourself, you can get the values, and you can compare the result with my values, right? So this is your slope now, this is your initial value 0, x naught is 0 and y naught is 1. Now here in this part you have to calculate the value of y1, y2 and y3, right? So these are y1, y2 and y3. So as we have done in previous example, there we have found y1 and y2. So here we have one more step to find y3. So in the similar way as we have done in the previous example, you can find all the values and you can compare these values and tell me whether the values are correct. Next category in single step methods is Runge-Kutta method. So first of all, I want to tell you that why we need these methods, Runge-Kutta methods. Very famous methods, worldwide famous methods. Any problem in today's world is assumed to be solved by Runge-Kutta methods. Everyone use this method because these methods are so accurate. First of all, when we have Euler methods and when we have Taylor series methods, then what is the need of these methods? Because uh, as you have done in your previous examples, you have learned that Euler method is not so accurate. So to achieve accuracy, what you have to do? You have to reduce your step size. So when you reduce your step size, your length increases. Similarly, you have also seen that in Taylor series method, we have to find various derivatives like y1 dash, y1 double, y0 dash, y0 double dash, triple dash, fourth derivative. And to achieve accuracy, we have to increase the number of derivatives, right? So let us take one example that y dash is equals to, say suppose y minus x over y plus x. One question is there which in our examples. So if we take derivatives of that part, and suppose if we want to find the fifth derivative or sixth derivative, so it will become very difficult, right? So Taylor series sometimes fails, not due to you can say method, but due to calculations. So calculations become harder. So we need one more method which is more powerful uh, as compared to these methods, in which calculations are easier and accuracy is higher. So that category is Runge-Kutta methods are developed by Carl Runge and Willem Gutte. These methods are well known by their short names, Runge-Kutta methods. In short, RK methods. They they followed Taylor series solutions up to rth order. Means if I am saying Runge-Kutta fourth order method, it means they are just following Taylor series up to fourth order, right? Now, what is Runge-Kutta method actually? Fourth order Runge-Kutta method is known as RK method, right? So this is RK method. Fourth order Runge-Kutta method. Remember students, in your exam, if it is written Runge-Kutta method, it means it is Runge-Kutta fourth order method, right? Now, what is the technique of this method? In this method, we will calculate the next value yi plus 1 with the help of yi, and these are the four constants which we have to evaluate one by one. The value of k1 is h f of xi by I, the value of k2 is h f of xi plus h by 2 and yn plus k1 by 2. K3 is h f of xi plus h by 2 and yi plus k2 by 2, and last we have k4 h f of xi plus h and yi plus k3. So you can learn this formula easily. You can see in K1 there is no shift, that means no step taken forward. In K2 we have taken half step. In K3 evaluation we have again taken the half step, and at last for K4 we have taken the full step. So one example over this fourth order Runge-Kutta method. Here we have given slope 1 plus x by t. Instead of y here we have x, and instead of independent variable t x we have t, right? This is our boundary in which we have to evaluate this initial value problem, right? So initial value become 1 and we have to find the value up to 3 here. So this is your initial condition, that x1 is 1, means to say, that means at t1 we have given the value of x equals to 1. So we are we have to take the step size as here h equals to 1. So this is our solution. So as we have done, as we have learned previously, what is the formula? K1, this is our K1, hf of t naught x naught, right? hf of t naught x naught. So what is the value of t naught? T naught is, what is t naught? 1. And what is x naught? That is also 1. So we have substituted t naught and x naught in the formula. So we get the value of K1 equals to 2, right? Similarly, in the other formula, K2, K3, K4, you can substitute the values and get the values of K2, K3 and K4. After getting all these values, K1, K2, K3, K4, you will substitute all these values here in this value to find the value of Y1. So working is very easy. Just you have to remember the formula, right? This is another example I have taken. So in this problem, what is given to us? The value which we have to find is y 0.1 and another value we have to find y 0.2. So what is given to us? Step size given to us is 0.1 and initial value is given to us x naught equal to 0 and y naught equal to 1, and this is the slope is given to us, right? So as per formula, K1 is h f of x naught y naught, K2 is h f of x naught plus h by 2 y naught plus K1 by 2 as we have learned previously, K3 h f of x naught plus h by 2 and y naught plus K2 by 2, half shift, no shift and full shift. You can remember the formula like this: no shift, half shift and full shift. So just substitute all these values. This is your x naught, this is your y naught. Substitute h as well. So you can find the values K1, K2, K3 and K4. So by substituting these values in your formula, this is K1, K2, K3, K4. You substitute all these values here in your formula, you will get the value of y1, right? In the very similar way, as you have placed here knots, so you can see knot. In place of these knots, you will place 1, then you will get the value of y2. So see. So again I have left this part for student, and you can calculate. You can see the value comes out to be at y 0.2 comes out to be 1.1682. You can compare this value and tell me whether this is correct or not. Now, after single step methods, we have next category, multi-step methods. So again, why? This why is very important. When you have whys, you can learn better, right? So my opinion is always ask your teacher questions, always ask the doubts, right? So again, multi-step methods. Why we need multi-step methods when we have Runje-Kutta method, when we have other methods as well? So the answer is accuracy. So we need more accurate results, right? So you have seen in Runje-Kutta category, we have only evaluated the value of yi plus 1 by considering the values of xi and yi. So no previous value, no previous step value we have involved in the solution. Now if we involve the previous step values as in our solution, we will get the more accurate results. So this is done by the multi-step methods category. So let us learn. We have mainly two multi-step methods. One is Milne's method and another one is Adam-Bashforth method. Now you can see one term here written, predictor corrector. What is that? When we solve multi-step methods, when we find calculations over these methods, we always have two steps. In one step, we will predict the value, and in another step, we will correct that predicted value. So that's why this category, you can see this category is known as predictor corrector method, right? So see, predictor corrector methods. So multi-step methods are predictor corrector methods, right? We have two methods, Milne's and Adam-Bashforth methods. Milne predictor corrector method. So these are the formulae for predictor and corrector by Milne's technique, right? So you can see here, not only yi, we are using yi minus 1, yi minus 2 as well as yi minus 3. That means for evaluation of yi plus 1, we need 4 step values. See, at the step I minus 1, at the step I, at the step I minus 2, and for the step I minus 3. So previous 4 step values we are taking to evaluate the value of yi plus 1, right? So after finding this predicted value, you see, we will substitute this value, predicted value, in our formula here. See, right? So we will substitute this predicted value in this corrector formula to enhance the accuracy, to make our result more accurate. So that's why these multi-step methods works in two steps. One is prediction and another one is correction, right? So this is one example by Milne's method. Here we have given slope y dash equal to x plus y, and we have given the previous 4 step values. This is our y naught, say suppose x naught, this is our x naught, this is x1, x2 and x3, right? Now see y2, if you just see your table, what is h? You can tell me. Yes, you are correct, h is 0.5. Now see yourself, 0, 0.5, 1, 1.5, the next value should be 2, right? So if you assume 2 as your y4, right, then these values are x0, x1, x2 and x3. So at the points x0, x1, x2 and x3, the values of y are given y0, y1, y2 and y3. So we will use predictor corrector method, Milne's predictor corrector method, to find the value of y4. So as we have learned, learned that we first predict the value and then we will correct the value. So this is your prediction first of all, prediction formula. Now see, this is your prediction formula. We just replace n by 3, right? So if we replace n by 3, we will get y4p is equals to y0 plus this formula. Now all these values which you have given in your table, you just substitute all these values here. This is your y dash, right? You will substitute x0 y0 to get y0 dash, x1 y1 to get y1 dash, x2 y2 to get y2 dash, right? These are the values. See, you will substitute x0 y0 to get y0 dash. To get y1 dash, you will substitute the values x1 y1. To get y2 dash, you will substitute x2 y2. To get y3 dash, you will substitute x3 and y3. So all these values, when you substitute, you will get the values of y0 dash, y1 dash, y2 dash and y3 dash. So substitute all these values here, you will get the desired predicted value, right? So after predicting the value, now we have to correct the value. So see, after substituting all these values in the formula, we have found the predicted value. This is our prediction, right? Now after this prediction, we will substitute this value here. This y4 we will substitute here, right? So again y4 dash is as per your given slope x4 plus y4. So we will substitute x4 plus and y4 in our slope, we will get y4 dash. So after getting y4 dash, we substitute the values here. So you can see we can find the results. This is our solution now. So this is your corrected value, right? Now if you want to improve the accuracy, if you need that, say suppose you have some system in which you want more accurate values, what you can do, you can resubstitute this value of y, this y2 means y4, you can resubstitute this value of y4 in your corrected formula, corrector formula, to get more accurate values. You will get more accurate values, right? Next method we have Adam-Bashforth predictor corrector technique. In this technique, the formulas are very similar to Milne's predictor corrector, just the differences of formulae, right? In this method, we have predictor formula as this and corrector formula as this. So only problem you will face to learn this formula, because coefficients are very large, right? Nothing else. This is very similar to Milne's method, just the difference is of formula. Yes, one more difference is the accuracy. Accuracy of this method is very, you can say, very good. So one example, in the similar way, in the previous example, as we have done in previous example. So again, I have taken the same problem, same example here, which we have learned in the previous Milne's method, right? So same example I have taken to compare the results. So see, again same cheese, x0 given, x1 given, x2 given, x3 is given, and y0, y1, y2, y3 is given to us. So again, in the very similar way, we predicted the value of y4 by applying the Adam-Bashforth technique. We have calculated y0 dash, y1 dash, y2 dash, y3 dash. So after finding all these values, we substituted the values in the Adam-Bashforth technique. This become our prediction. So this become our prediction of fourth y4, right? So after getting predicted value, we will correct the value with the help of correction technique. So this is correction technique of Adam-Bashforth formula. So just substitute your predicted value here, you will get the corrected value. Now see the results. This is your y2, this is your y2, this is, one minute, this is your y2 with the help of Adam-Bashforth. Now let us see, just remember 11.7656, and this is your value by Milne's method, 11.7659. So very less, difference is very less, but the difference is more accurate, right, as compared to Milne's method. You can compare the results with exact method also, right? So these are all methods to solve differential equations, ordinary differential equations, right? So one more category we have partial differential equations. So I will put one more video for that, and guys, subscribe my channel and like and follow.